Hi, in last video we saw what is oracle. Now let's see what is phase kickback in quantum computing, and we will use these concepts in upcoming notebooks on quantum algorithms. So before looking for phase kickback, let's see what is C naught gate. So C naught gate looks like this, and here we have Q0 as control qubit and Q1 as target qubit. Now if control is 0, then target is left as it is. As we can see here, this Q0 is 0, so target is left undisturbed. However, if control is 1, then we just revert the bit, or we flip the target bit. So here we see control as 1, so target is flipped to from 0 to 1 and from 1 to 0. So that's how this is the normal behavior of C naught gate. Now there are some cases where instead of flipping the target bit, uh, instead of flipping the target bit remains unaffected, but control bit gets the phase of target. Or in simple language, we can say control is expected to remain undisturbed, but control gets affected and target remains unaffected. So example of that operation is if we make plus state as control and minus state as target, then in output what we see that minus state is left as it is, but this control, which was supposed to remain as it is, it got converted to minus, means it got the phase of target. Now let's see how it works mathematically. So we are applying C naught to the plus and minus state. So here we have C naught plus minus. Here we are this Q0 is written on left side and Q1 on right side. Now if we expand this, then this will become plus state and this will become minus state. Taking out we will do the tensor product first. So after doing tensor product, this will become 0 0 minus 0 1 plus 1 0 minus 1 1, and this 1 upon root 2 1 upon root 2 will be multiplied as 1 upon 2, and then here we will apply C naught gate. C naught gate will be individually applied to the each state which we see here. So applying C naught gate, this one and this one will remain unaffected, but here target will be altered. So here 0 became 1 and 1 became 0. Now from these two terms we can take 0 as out. From these two terms we can take 1 as out and write it like this one and this one. And if we see this term, it's 1 minus 0, and here we saw that we can represent minus state as 0 minus 1. So if we take minus out, then it will become 0 minus 1, and then we can, I think, what is this step? Here we have taken 0. Yeah, this is the step after this. So here we taken minus out and it became from 1 minus 0 to it became 0 minus 1. Again we can write it like this. We can take this 0 and then minus 1 and this 0 minus 1 like this, and this 1 upon root 2 can be splitted between these two terms, and these two terms become equivalent to minus minus. So we can say that C naught of plus minus is equals to minus minus. Here is minor mistake. It should not be C naught of minus minus. Instead it should be just minus minus. So C naught of plus minus is equals to minus minus. So now we proved it mathematically, but You might think why this happens. So it happens because here we are applying C gate on states which are already in superposition, and this gets entangled with each other in such a way that targets get affected, sorry, control gets affected by the state of target. So we can think that all fundamental concepts of quantum computing like superposition, entanglement, and interference are responsible for phase kickback effect. And now let's see the demo of actual circuit. So for that, we will use this qmod language and just hit on this synthesize button. So here we can see that Q0 is in plus state, and Q1 is in prepared in minus state, and this plus and minus state are passed through this C naught gate, and here these two will be in the minus minus, but since we can't measure the minus minus state, we are passing it to headmat gate so that we observe 1 1 here, and it will confirm that here it was indeed in the minus state. So let's execute it, and in output we should get 1 1. Yeah, indeed we got 1 1, AS1 and BS1, which confirms that uh, after passing through C naught means at this phase it was minus minus. So this is what phase kickback effect is. Here phase kickback is happening, and this is the measurement part which we saw, and yeah, we saw the output. Okay, so now let's see phase kickback in oracles, or also known as phase oracle. So if we combine the concept of oracles which we saw in last video and concept of phase kickback, then we get this phase oracle thing. So we saw that in quantum computing we can represent oracle like this, where inputs are x and y and output is x and XOR of y and fx. Now if we hard code this y as minus state, then similar to the last example we saw, we get this minus state as it is here, but our primary qubit will be affected because of the state of this minus, and it will be affected such that this minus one is attached to this x. If fx is 0, then this will not be attached, and if fx is 1, then it will be attached. So that's how phase oracle works, and how it's coming. This is a mathematical proof which you can go through. It's similar to the last example which we saw. We are just doing, applying the formulas of oracle and doing mathematical calculation. Now let's see how to implement phase oracle using Classiq SDK. So for now I will take x as 0, and since we are going to use arithmetic oracle function of Classiq SDK, we will have this one as hard coded as -1, and in output what value of output we see, it depends on what expression I take. So I am taking x as 0, and fx I will take is x less than 1. So yes, x is less than 1 means fx will give 1 in the output, and we should see final output as -0. But since here our here minus is the global state, in Classiq output we will see only 0. Now important thing here is that we are not seeing any change in the input. We are getting 0 as it is here in actual output, but that's not no need to worry about that. We will see it in next notebook when we see Deutsch algorithm. But for now, let's see how to implement phase oracle to get the understanding of SDK. So here I had imported arithmetic oracle, and expression I am passing is x is less than 1. Input qubit side, I want one, means this one q0, and its name is x input register. And then I'm applying arithmetic oracle, and this part is handled by arithmetic oracle. It's part of arithmetic oracle, and then I will synthesize and execute it. So first it will just synthesize, and we will execute in browser here. Okay, so now we can see that this is our arithmetic oracle, and this is the input register x which we specified. Now if I expand arithmetic oracle, then we can see that this part is automatically taken care by arithmetic function. And if I expand further, then we can see this one. This part when the student while seeing oracle, why we have two subtractor here. So this is just to keep the circuit reversible. We will not go in much detail, just execute it. And in output we will get 0 as expected. So this 0 is for q0, and this is for the extra qubit for by. So this right one is the value of x, and we are seeing it as 0 because the reason which we saw, that phase will be the global and it will not show in the output. So that's how we can implement phase oracle. Now let's see the task. So you should stop the video here and try to solve these tasks, and then come back here for the answers if you have any confusion. So let's start. In task 1, we are applying C naught gate for minus as control and plus as target. So for this one, output will be nothing. Output will be unchanged, means output will remain minus plus. For this one, output will be plus plus because control is also plus and target is also plus. For third one, since control is minus and target is minus, target will phase of target will come to the control, and minus minus will become plus, so its output will be uh, plus minus, like this. Now for creating the phase, or try to create phase oracle circuit using Classiq Python SDK. So for this one, uh, you can just use this same code, this one, and first expression is x less than 1 and x is 1. So to make the state of x as 1, you can refer back to the oracle circuit notebook to see how we can prepare state of x as 1. By default it's 0, and same case for all. Just need to update the expression and uh, do the state preparation of x. So that you can refer, for this you can refer that oracle notebook. And let's move on to optional task 3. So this optional task 3 is nothing but Deutsch's algorithm, which you can try for now, but if you find it confusing, we will see it in next notebook. So this was video on phase kickback and phase oracle. Thanks.